Alright, so let us begin again. I wanted to draw your attention back to this choice of controller where I have clearly articulated that when you talk about simple sense and send kind of application, you can be talking about a single processor. Whereas if you are looking at much more serious applications, then those applications essentially will require multiple processors. Okay. Now the point is that often you will be wondering why this what are these applications which can be highly demanding, right. Now one of the things that we can think about is industrial IoT. You will need this for industrial IoT applications. So I will call it IIoT applications. Okay. So that is one thing. Anything that has societal and economic importance such as industrial IoT, when you talk about that, you talk about the industrial process control, and you talk about process control and also supervision. Okay. Then environmental and structural monitoring. Okay, very demanding applications. Then personalized medicine, personalized medicine. You can go on like this, folks. Several examples can be given. Okay. Then home automation, traffic control and so on. So all these do not really come under the sense and send application anymore. Okay. So that is the key difference. In sense and send you are just doing extremely simple activities, quite trivial in that sense, and they are extremely low power. They can work for the required 10 years of lifetime and so on. But these are so those applications are one type. So if you have to choose a controller going away from the simple sense and send kind of applications, actually for sense and send we can talk about some controllers, and I will write down a few. Telos B, for instance, you might have seen Telos B, then you might have seen its predecessor Mica 2, then even its predecessor is Mica Z, then Iris. All these are mote class devices. They used to be called motes, 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 simple motes. Okay, 16 megahertz kind of processors. In fact MSP 430, a very well known processor, is actually used in Telos B, and it is used for those simple applications. Those are one type of applications, but then they are not the kind of ones that can be applied here, and I will have to motivate ourselves why you need a multiprocessor and what are the limitations of these existing ones. Let me draw your attention to the earlier, very quite earlier years. See, writing an embedded code used to be hard. Okay. It moved away from embedded code in terms of writing assembly language, assembly code. It moved away to writing it in some sort of a C language, right. You write it in C and then you use a compiler, isn't it, so that you are comfortable in writing in C code. Alright, so this has been something you can do that and then dump that code. So you could simply dump that code, dump the code on the flash, dump the code. Another way is okay, you can do it this way, but then if you have to maintain timers, it used to be very hazardous. You have to manage the timers yourself and you have to write the code managing timers. So I will say dump the code, how to manage the, so how to manage the timers, how to manage the other resources, memory for instance, okay, and also CPU. All this you have to manage yourself. That means as a programmer you have to keep track of everything. So people went ahead and said this is going to be very hard, let us start developing in using an operating system. So people came up with TinyOS, Contiki, then real time OS, no, I think it is called RIOTS, RIOTS, okay, RIOTS or Riot, it used to be called Riot operating, so on. So many operating systems were there. So the operating system's job would be to manage all these timers and other resources and all that and provide an abstraction to the programmer. But to be honest, this is very difficult for any changes that you want to do, okay. For instance, even the people who develop this compilers for these for these operating systems to run on these mighty modes, I mean small modes, have not been very successful in providing a foolproof way of ensuring that performance is sort of extracted to the maximum, okay. So that has been the problem. For example, developing software for heavily resourced hardware platforms is quite labor intensive, and the coupling of the functional and non-functional properties are quite hard. So I will tell you why these operating system based embedded systems where it is very hard for us to manage. Let us take an example, otherwise we will never be able to get to that. There is one problem of this kind of single processor based approach, including an operating system, particularly with respect to resource. In fact, you have resource interference, okay. Think about the following, folks. Think about a single controller which has an ADC and it is connected to a standard. This is a picture that we know very well, right. This is the ADC and this is the well known radio, and all of it is part of the SOC. This is ADC here, okay. If you look at this picture closely, you will realize that supposing this is high sampling frequency, you need very high sampling frequency here, okay. It could be, let us say, acoustic microphone, okay, acoustic. If you are using an acoustic sensor like a microphone, you will be sampling at very high frequency, right. And if you are using these acoustic sensors for, let us say, what we described as previously the issue related to structural monitoring. Now you see I am trying to retrofit single processor for structural monitoring. So let us see what actually happens, okay. So I am using it for structural monitoring. Now the issue will be the following, okay. Because you have a single processing resource, MCU needs to handle, let us say, some time critical events, okay. What are those, folks? Now comes the story, okay. Now comes the story. This is your bridge or some structure that you want to monitor, and you have put embedded sensors at different places. Depending on how long or how big your structure is, you would have put embedded sensors, and they are all communicating, isn't it? They are all having communication units. I will just show them by some radio, okay. Right, this is your structure, Now see the problem. Here in this picture, this guy is doing high sampling frequency, this SOC ADC. At the same time there are signals coming from this one, this is A, B and C. There are 3 nodes here. B is giving some data to A about something, maybe it has sensed some anomaly and it is passing that information to this A. A has to respond in, it is a time critical operation, it has to respond in a given deadline, So it becomes time critical. Okay. It is almost impossible folks, even if you have the best OS running, to work on this single processor environment, because you have to, here what happens, this time critical event in this case is coming from where? It is coming from the radio. So the same processor is looking at, should it look at radio or should it look at the sensing that you have connected the sensor, the high frequency sampling that you have connected the acoustic sensor to. Both are conflicting in requirements. Therefore what will happen? CPU resource will get into interference. So this is a problem which cannot be easily solved if you try to look at the single processor situation. Okay. You can also take another example, let us take another example to convince you. Okay. Let us take one more example, example 2. Okay. In the second example, you suppose that the application requires a node to react timely to events. For example, you have a sensor node, okay, then you have several, let us say, GPIO pins, and to one of the GPIO pins you have connected a relay, and this relay has supposed to do a actuation, has to perform an actuation, okay, and this is a timely event. It has to happen within a certain time. It has to quickly perform an actuation, and so again you have to receive the data over wireless, and within a certain latency, within a certain bounded delay, you have to issue the actuation to the relay. The relay command has to be given so that it can get actuated in quick time, in within the required time. These kind of things are not going to work even if you talk about a single processor with an operating system. So you can summarize and say, with an OS like TinyOS or Contiki and so on, whatever application you develop will be fragile, it will be monolithic, and maybe sometimes you may even over provision. Some of the systems. So making it extremely difficult, these over provision systems, making it difficult to debug. You will have problems of debugging, maintenance and so on. All these issues will come up. This, I am sure, has motivated you to say that let us look at multi-core systems. Okay. Let us look at multi-core systems, but that is still some distance away. Okay. Because now you are actually, we deviated the topic. We said let us see how to choose a controller. From the choice of controller we went to motivate ourselves why you need multiple controllers. Okay. So we haven't still answered that question, how to choose a controller. So again I will go back to our slide here. Okay. So now this is done. We now know why you need single and multiprocessor systems, at least that is clear. Now let us look at the parameters associated with the choice of the controller. See folks, I did talk to you about the processor's data sheet which clearly talks about the microamps per megahertz. What is the kind of current consumption? Typically it will be in microamps per every 1 megahertz of the processor clock. Okay. What is the current consumption? Now clock is an issue and we should go into some detail of the choice of the clock on the controller. So again let us exit and go into this direction, which is what should be the clock source for the controller. See, this is a course on design. So you should know, if I have to choose a controller, why do I need 2 processor controllers? Why should I choose, what should I choose as my clock source and what is its implication? Okay. Then you should say, yeah, then that is definitely one way. The other way is, how does this processor compare in its performance? Then what are the typical applications of multi-processor and single processor applications? Are we going to put it in industrial applications, or are we going to do it for control and supervision, or is it structural? What is the kind of application we have in mind? That will actually determine the type of controller that you are talking about. So now let us get into this clock source, which can be any of these 3 different types. If you look at clock selection, okay, now let us do that clock selection. Let us do clock selection. Okay, clock selection. The clock selection, again there are 2 things that we are doing in this course. Very carefully if you observe, we are trying to try to look at low power, and we are also looking at sensing. Every time it comes down to sensing. Clearly anything that you do in this course particularly, it will have implications on power, it will have an implications on sensing. That is why we discuss so much about the ADCs and so on. So again clock selection is back to sensing as well. Okay. Now the clock usually has to be stable and there should be no jitter. Okay. Because this jitter, what does it do? It impacts the signal to noise ratio of the ADC. That is the problem. So if you have higher SNR, what does it mean? You have more of signal and a very small amount of noise. Essentially you will have no problem. A higher SNR means there is more signal. So coming to the point, clock jitter results in sampling, the sample will actually have a skew in the sample. So you have an ADC standard picture and you have a sensor connected. If there is jitter, this is ADC. Let us write it neatly. I am just showing you the ADC block. This picture has to be made ADC, and then one of the channels I am connecting a sensor, it has to be joined. Alright. So the jitter, if you have jitter in the clock, so clock will be fed to the ADC, this is the clock. Who is generating the clock? Clock is coming from either internal clock, or it is an external clock, or it is onboard generated clock. That means you have a crystal oscillator clock which is external to the CPU, to the SOC, but it is not external. Means external has 2 connotations. One is the clock, it is not part of the board itself, it is coming from some other source, maybe some other clock generator. Let us say you are talking about 2 boards, Okay. This clock is coming from another board, board 1 and board 2. This is where your controller is, this is where your radio is. Okay. This block is purely a oscillator block which is outside. Okay. It is not part of the board. This is one type. Second type is no, this is too much, there is no that kind of space. I will generate the clock using 2 pins over which I can connect the crystal. This is second type. Third type is oh no, this is also too much of components, let me use internal. Now here is the problem, but you can always use internal, right? Why do you want to use crystal oscillator outside or you want to use external oscillator? All of them will have a bearing on the sensing. This is the key point I wanted to tell you about as far as choice of the clock source is concerned. So let us now go back and look at what are the issues associated with the jitter that comes from this. See, as long as the skew is small, let us say the skew is small, okay, small compared to sample rate. Okay. If it is small compared to the sample rate, then it does not matter, no problem, I will simply say no problem. Okay, it does not impact much. But the higher the input frequency, signal frequency, the more jitter reduces the SNR. This you have to be very clear. Okay. Why are you choosing small, very small skew compared to small compared to sample rate? That is because your input frequency may be very low, maybe even close to DC, in which case you will not have much of an issue. But if you have an input signal frequency which is quite high, then more jitter, if you have more jitter, so I will say input frequency of signal, let us write it in the next sheet, I think that is better. So let us say skew is impactful, is skew impacts sensing via the ADC if the input signal frequency, is high, I will simply say is high. Okay. Then it will pull down the SNR. Now you can look up several data sheets to come up with what may be an ideal jitter that should be there. People talk about jitter in picoseconds, jitter, clock jitter. This is in picoseconds, you will typically talk about 1 picosecond or 1 nanosecond, right, 1 nanosecond and all that. Okay. So careful, 1 nanosecond. So be careful about the drop in SNR. So you can draw a picture now and you can put it in log scale. You can put SNR in log, okay. We will normally express it in dB, log scale, then you will have a drop as you increase the frequency. As you keep increasing the frequency, I did not show you in logs, I am just showing you that the whole thing is in it is a log scale. Obviously this must be the 1 picosecond and this must be the 1 nanosecond. Okay. So you can see that performance can matter a lot. What does it all mean to us? It simply means if you choose external clock, okay, what is the jitter? It will be the lowest, I will say external, I will simply say jitter, okay. It will be the lowest, it will require a crystal, of course it will require a crystal, that means more components, and any crystal oscillator is associated with higher power. So you see everything is boiling down to sensing and power, sensing and power. So this will come down to higher power. And one more nuisance with the crystal, it takes longer to start up. Supposing you put the controller to sleep, you are using an external crystal and you put the controller to sleep, what will happen? The crystal has to the crystal oscillator has to come up, that oscillator block has to come up, and then it has to start giving you the clock signal. Now that takes time, and during that period you cannot do anything, number 1. Number 2, power consumption also will go up, these problems will be there. So you can choose the external clock carefully, whether you want to do it that way or not, but I can tell you for sure this give you the best performance. Fantastic, right? You are the best solution on hand. Then you can also do medium jitter, okay. In the medium jitter case, this also requires a crystal, but this crystal is where it is just placed outside the SOC. In this case you do not know where it is coming from outside the board. So please note, external clock means it is coming from outside the board. So I will say outside the board. You are generating a fantastic, very stable clock, and then you are bringing it. I mentioned about board 1 and board 2, if you recall, it may be coming from board 1. Here in medium you are still doing single board, and same problem will come. You can put ditto here and you can put ditto here, longer startup and all that, okay. Okay, yeah, but then if the application is still the same, right, the jitter is medium, that means again you have to take care of safety margins, whether it will impact the sensing or not, the quality of the signal that is sensed, is it impactful or not, will have to largely depend on what you want to do, okay. Now the third one is lowest, medium, and the other one is highest, right. Internal oscillator, if you choose, this will give you the jitter, which is jitter that will give you the highest, jitter, but advantage is no external components. And it is good if you are talking about simple sense and send. So again it is connecting back to sense and send. Okay. You have simple low frequency signals, almost DC, okay. Then you do not have problem of low frequency signals. Well, you can go on like this and talk about controller and implication of ADC, implication on the reference for the ADC and so on, but they are all little bit out of place here. We will not talk about that because I wanted to concentrate back on to get you back here on track here. So folks, now you see we exited here, we have to come back here now again, okay. And when we come back, we realize that the story does not end here, you have to go back and look at benchmarking also. That is the third thing that you may have to worry about. See folks, benchmarking is another story, okay. Now when you talk about benchmarking, how will you choose the controller from a performance perspective? That is what you want to do. Supposing you have a certain time period, this is time period, starts from 0, it stops at t, okay. This is your time period. Now what is the, you are asking the question, what is the amount of work done in this period, okay. That is not a trivial question, you cannot answer that question. I will tell you why. Supposing you have a compiler, now compiler, it is actually dependent on many factors including compiler, it will be dependent on how the compiler was designed, it will depend on the different libraries, right. It will depend on the wait states if they were introduced, wait states, and what about background activity, okay. Background activity, what does background activity mean? What about DMA? Maybe DMA is happening in the background, okay, right. And so many things have to be looked up when you talk about this question, if you want to answer this question of what is the amount of work done in this time period. So it is almost difficult for you to arrive at something useful. Now it does not end there. People have proposed two ways of sort of benchmarking CPUs. One way is to use what is known as Drystone, 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 okay. But unfortunately this Drystone is, I think, interferes quite a bit into the compilers, okay. It interferes quite a bit into the, it is more useful for compiler writers, not so much for compiler writers, I would say. So this arrow is to be replaced by saying, yeah, you are good, but it is for compiler people, not to benchmark a CPU, okay. Because time it takes for executing a library function is actually not accounted in Drystone, because it is going out somewhere and picking up something, and then the whole thing is not easy. That is one part. Second part is they do not look at, they do not give you any simple way of source code, the source code and the reporting methods, both have a problem because they are not standardized. So this will create standardized, yes, it is not standardized. This will create a confusion in the minds of people when you do not use them in a uniform way across processors. So the newer standard that has come up is the core mark. Core mark. Good thing about core mark is it is just talking about CPU core. It is just talking about the CPU core, and this is very important. All the computations are run at made at runtime, all computes. So here you see, so no question of going to a library function and all that. You do all computations at runtime, which is not the case in Drystone. If you put this condition, compiler is actually stuck. Okay, you can't get in the compiler, you can't do any escape out for the compiler because it can't cleverly solve the problem of if you are doing this at runtime. So it is mainly focused on, this core mark is mainly focused on integer operations. Okay. One other thing is, we mentioned about the use of standards in a standard way, which was not the case in Drystone. Okay. Both the source code that is used and the reporting methods, that was a problem. You had to somehow include the name. Okay. Each benchmark should include the name and version. You must include the name and version of the compiler. You have to disclose for sure. You must put down the compiler flags, you must mention that. That way you will catch, right. Full disclosure should be possible. Full disclosure, no hiding and so on. Okay. And therefore, so you are more or less you can't go around the taking advantage of compiler and compiler library calls and so on. You can't do that because everything is done in, as I mentioned, it is in real time, in runtime. So the way core mark works is, it takes very standard operations. Okay, it considers a set of standard operations. It could be matrix manipulation leading to some linked lists, leading to a state machine, and then maybe CRC computation. Okay. When you do things like this, it is almost impossible to overcome the effect of compiler. So no effect on, difficult to overcome the effect of compiler. Okay. So that is the good thing about the core mark. So folks, I want you to go and look up the website, core mark website. Okay, it is rich in information, and choose it, use your benchmarking, whatever, if you wish to benchmark, do look up those codes, run them and decide on the performance of the CPU. Okay, this is very important. So of course the core mark is highly dependent on clock rates, there is no doubt about that, but that is where you are trying to differentiate between one type of processor and the other, is not it. So you must look at this website, core mark website, to give a understanding. But I must also tell you that things are not just as simple as what you think. there are other things also you have to consider. Okay. One of the things that people are looking up in terms of core mark is performance per milliampere. Everything revolves around the current consumption. This is becoming very, very important. Okay. Microwatt consumptions are playing a very important role in deciding on the how many microwatts per megahertz does it take, for instance, is something that people are worried about.